property of rho is that there exists 3 stones that are not in QP. And they are mapped to Z by rho. So rho ijk is Z. So what's the so what's the property of rho? The random function has this property. Is if if an adversary gives you a variable and some small set of forbidden stone, you can still find a triple, the pre-image of this variable that is not in the set forbidden set. So somehow each variable has a lot of pre-images, and it's a simple counting argument. This I acknowledge at our paper. I use this with a little bit different constant, but like asymptotic with the same. And it's because like the number of these variables is n squared, and the number of triples of stones is n cubed. So.
And if you choose a random function, you just distribute the triples of stones.
This is like a 3i group.
Really, where the stones play a role.
Yeah. That's we need some of the number of stones to be bigger than the number of variables, or the number of that's okay. So we have this rho. So by the we are in AP, right? We suppose it's alpha foolable, so the closure is alpha foolable. And for variable Z, we have this triple ijk, right? So we apply this lemma that the new so from this lemma we have this new gamma assignment falsifying ijk or rho ijk or ijk or not rho ijk. Right, and this ijk is given by the property of rho. Right, so these rho ijk is actually D and
Yes.
Jak mało wiadomo, przecież to jest nie. You też pan wie, co takiego nie pan. Jak może
we can be here.
Yeah, we can.
Okay. Good. So because alpha p is alpha foolable, so we change alpha outside the closure of AP to some gamma, right? Which falsify, like we change the stones and it falsify only one of these two formulas, right? How we pick this ijk is by row. That this row ijk is our z, right? Because we change alpha has a preimage in AP. We change alpha only outside the closure, so gamma has a preimage in AP. So gamma is also or like has a preimage in AP. Right? There is some beta. This beta, so we have this beta. This beta needs to end somewhere. Is a property of the affine
beta prime. So the beta that corresponds to gamma, let's say.
Yeah.
Because there will be the beta that corresponds to alpha, which
Yeah.
is different. Yes.
But
The only clauses are those two, and those mention z, so you're not.
Yeah. And so like it now the things about listing, right? It's some clause, right? This clause was introduced only by think of these, right? So it's some clause which arises when we like these things, but every clause, as I said, contains all variables of blocks, right? So far from Z, we know that somehow it contains a block of Z, right? But we want to prove it's about Y, but we know that if there is a block of Z, there is any variable mentioned in there. So
Right. So the mentioning will say the variable is 0 or the variable is 1. It's one of the pre-images.
yeah.
I see. So 2 years ago, it's told us this. Oh.
So this is the proof of the equation.
These z's were also replaced by some inner products.
Yeah.
All right. Every variable
So now finishing the proof of this, right?
That's what I'm interesting.
Yeah, so this was the place where obfuscation map was used, the only place. And let's continue with the proof. So let's take a space U, which is somehow the span of all linear constraints that are in S. The formal, let's look on something S. Right, there is some affine space S, and it says affine space S is like MSX equals CS. Right, so the space U is a span of union of all things in S and row space of
Sorry, what? Sorry, got distracted.
So look at the affine spaces here, right? Look at one particular affine space. It's defined by the system MS times X equals CS, right? Take all these matrices here, right? Take the row space, do the union, and do the span. The thing is, what are actually these affine spaces are actually cubes, right? Because it's a this affine deck arises from a proof. So these are basically the negation of clauses of the formula. So these are cubes, right? By this claim, right, each variable is mentioned somewhere, right? So dimension of the U is actually Boolean. It's n times b. Because what does it mean? Like a variable y is mentioned.
Yeah.
It means y equals 0, or the constraint y equals 0 or y equals 1 is present. Right? So this has a full dimension. Okay. So now we almost know that we never used so far that our deck is a bottom regular, which we will use now. So let's define difference space W, which is a span of row space of MP. So this AP is defined MP times X equals CP. So take this and post P. So take the constraints that are in AP and take any query that is made after P on anywhere. Take the union and again create a space.
Yes. Okay. At this point.
It does not have to be. Now, what says the bottom regularity of post P? So the bottom regularity says that the dimension of post P is at most the full dimension minus T. When T is this line.
Because none of the queries that appear there appear in post P. So they're all linearly independent of post P. That's it, right?
Yeah. Well, if, for example, if some query here appears in post P, right? So let's say here we have a linear query L and it's in post P. Then if we take like this U, if we take post Q, it's a superspace of post P. So we would have this is not.
Yeah.
So from this bottom regularity, we have upper bound for this. So this is at most codimension of AP plus n times B minus T. Right? And the thing is, U is a subspace of U of W. So it's from property of affine that U is a subspace of W because any constraints here can occur only as in a linear space when you from AP and the query you made to get to this. So if you have some constraint here, it has to be definitely in W. This, and by this we have this is smaller than W, but already W has a full dimension. So from this, we have that codimension of AP is at least T. And yeah, so one strange thing somehow is that somehow we can use some of this proof also to prove like the lower bound for top regular, right? Somewhere it breaks somewhere. We actually don't know like if top regular, bottom regular are different, say, don't know. And yeah,
Have you tried to show that you can solve this problem with top regular stuff? Is it also? I never thought about the problem. I have no idea.
yeah, I don't. No, we don't.
You think it doesn't work actually?
Like my guess, but it's really guess is they are the same.
The top regular.
Yeah, and bottom regular, yeah.
The bottom regular kind of makes sense here as a definition, at least from our view of DAX. It's kind of like saying, if you've already queried something, you can't. Or
Yeah, like we discussed that if this definition even makes sense, like so, and yeah, like the conclusion was yes, but because what does it say, right? That it makes sense somehow for the roofs in some sense.
not too clear, but top regular, I have like zero intuition for why that's a definition. Bottom regular has some kind of.
Yeah, I still there are quite a new notions, right? This variant of regularity was introduced 2 years ago, so people don't know much about it. And I think nicer art to explore. If you like,
I'll stop the recording.